All right, so, but we are going to start with the magnetic force. So we are kind of 1 week late, but that kind of means that I mean, some of the chapters I need to go through a little bit more quickly uh, than I have anticipated, right? So we are going to start with, in these 2 weeks, we will be seeing basically the magnetic field and the magnetic force. Uh, so first I'm going to describe what that thing is, right? So we have been dealing with the electric force up to that point. Now we have to face with this, the other aspect of electromagnetism, basically. And I will kind of try to explain what it is. And then I'm just going to give you this point of view of the field itself, the magnetic field. And well, after that, of course, we are going to see the applications. However, I know that you have seen these in high school, even in ÖSS exams. They ask questions about these. But here, it will be a little bit more mathematics there will be a lot of vector algebra in here because we are going to talk about the cross product a lot. Right? So in all aspects of the discussion of the magnetic fields, we will be seeing this cross product a lot. And so as a result, geometrically, the vectors will be these in the 3 dimensions. So as a result, this produces some difficulty because we have to draw the pictures accordingly and things like that. And so as a result, the discussion of the magnetic fields itself is a little bit more difficult. Something that you haven't seen before. And so as a result, at least these parts of the course is a little bit more difficult than the previous ones, okay? But in any case, let's just continue with this. So let's remember this electric force, right? We basically say that 2 charges, I'm just going to start with this. So this is just a reminder. So 2 charges apply an electric force on each other. So if you have 2 charges in here, whatever they are doing, it doesn't matter. We know that they apply these forces to each other, and the force is given by this Coulomb's law expression, right? So don't get confused by this expression. I have talked about this before, but in any case, I mean, it's just a very simple expression of the force between 2 charges, right? And let's just remember that the charges in here play the role of the coupling constant. So it is how strongly these 2 charges interact, right? It's basically, it tells you this. In any case, so we have the magnetic force is quite similar like the electric force, but it's basically 2 moving charges apply this force. So as a result, 2 stationary charges do not actually show any magnetic force. They only apply an electric force to each other. But if the charges, both of them are moving, in that case, there's an additional force applied on the charges applied to each other, right? I say additional because the electric force is still there. So that's one of the things that's complicated in here. So they still apply the electric force in here. They still apply this force equal to the Coulomb's law expression, but there's an additional force. So this additional force I'm going to show with this green color in here. So this is just symbolic actually. So as a result, I'm not going to, yeah, I'm just going to just choose 2 directions in here. So let's say it like that. Yeah, let's say it like this. This is F2 mug, for example. And so therefore the force on this thing would be along this direction. This is again arbitrary. So we expect that again Newton's 3rd law holds. So these forces are equal and opposite. I mean, normally we expect, but in any case, that's basically what it is, right? It's basically, it's an additional force between 2 moving charges. Okay. So as a result, we can actually think of it like that. We can describe it like this. And then the question is, what is the corresponding Coulomb's law for this case, right? Let's say it like this. What's the law of force? So how can I write down the force applied on the, for example, the magnetic force applied on the charge Q2, let's say, how can I express it? So you can kind of see that in this expression somehow, the charges will be there, because if there are no charges, there won't be any electric or magnetic force. Only charges somehow apply these forces. So the charges should be somewhere in there. The velocities should be somewhere in there, because if they are not moving, then there won't be any force. And what else? And the distance between them should be in there. So this R unit vector and whatever R should be in there. There should be an expression in here, but you can easily see that this is a complicated expression, right? It's not something that is as simple as Coulomb's law, right? So as a result, we don't usually, I mean, when we are teaching this subject, we don't write down an expression for the magnetic force between two moving charges. We don't. There are several reasons for that. First, it is too complicated. It's not actually easy to analyze the magnetic force like that, right? It's not just like it's not like the Coulomb's law. The second thing is that these are moving, which means they are changing their places. So therefore, the distance between the charges, for example, will change eventually. And this produces some other physical complications. This means that the force is going to change eventually, but I mean, there's something associated with the speed of propagation of the physical effects. So we are going to say that eventually at some point that this electromagnetic force actually propagates with the speed of light. So as a result, at a given moment, this charge Q2 is actually become affected by some kind of a past position of that charge Q1 somewhere in here, right? So as a result, there's some kind of a delay between the effects in here. So as a result, this makes the real magnetic force really complicated, okay? So as a result, we don't do this. What we do is basically similar to what we have done. So let's just, again, remember this. So for the electric force, right? Electric force. We actually invented the concept of the electric field. So let's say it like this. Charge modifies E field. And then we say that the E field applies a force on charge. So basically what we have said is like this. I mean, we have a charge in here, let's say Q1. We have said that this charge produces an electric field in space. So somehow the charges directly interact with the electric field. And moreover, what else? So if there's an electric field in here, which is probably produced by some other charge, and if I place a second charge in here, sorry about this, second charge in here, then there will be a force applied on that charge, all right? So that's F2, for example. Okay. So as a result, instead of describing this as a force between two charges, we basically describe it as an interaction between charges and the electric field. Let's remember this. So we say that the two charges do not directly apply a force on each other. That's not the case. But there's an indirect force. But essentially, all the charges are interacting with this electric field. That electric field that somehow fills all of the space. And so therefore, there are these two aspects of this interaction. One is how a given charge produces an electric field, whatever. And the second one is how an electric field applies a force on charge. So we are going to do the same thing for the magnetic force again. So we are going to argue that there is a magnetic field, right? There is something called a magnetic field that fills the space. Magnetic field. What happens is that I'm going to use the green colors for that. What happens is that a moving charge produces this magnetic field. So I'm just going to show it like that, all right? So I'm just going to write it down like that. So a moving charge produces a magnetic field. Okay, a moving charge. There is the second aspect in here. So that's the magnetic field in here. There's the second aspect. So if I have some kind of a magnetic field already produced by some charges, by some moving charges, and if I have a second charge in here, which is moving with some velocity in here, v2, let's say it like this, a magnetic field applies a force on moving charges. Okay. So as a result, somehow, there's this what we call as electromagnetic field actually. So there's an electric field and a magnetic field. So these are two separate fields. The electric field directly interacts with the charges, whether they are moving or not. But the magnetic field interacts with charges only if they are moving, right? So therefore, it's basically an interaction between that part of the field with moving charges. Okay. So as a result, we have to think of the problem like this. And so as a result, we are going to separate the problem of basically discussing the magnetic field like that. So basically this chapter, this is chapter 27, is about the magnetic force. Force applied by the magnetic field applied on a charge. So in any case, let's say that in chapter 28, we are going to see the other problem, how a moving charge produces a magnetic field, right? So in the first chapter, so we will not be interested in how this magnetic field is produced and things like that. We are not going to be even describing what that magnetic field is. Well, we will just accept its existence because we know that this thing exists, right? Somehow it is filling the space. It is, since it actually is not matter, it is hard to imagine this, but physically we know that this field exists. We have discussed this situation for the electric field. We are also going to claim that this field itself has some energy. We are going to find this energy expression later. And I don't know, in the third year, for example, when you take electromagnetism, you are going to see that this magnetic field, both the electric and the magnetic field has also carries some momentum and angular momentum as well. So as a result, I mean, this interaction in here, when magnetic field applies a force on the charge. The charge actually can also think of it as the action-reaction thing. So as a result of that, the magnetic field somehow changes as well. It basically gains a momentum in the opposite direction. So as a result, the Newton's third law is somehow satisfied actually. So there are actually these kind of aspects of that interaction too. But I mean, this is the most important picture. It is essentially the interaction between particles and what we call as the electromagnetic field, right? So this interaction has these two aspects. The charge particle, well, a particle interacts with these fields only if it has charge first. A charge interacts with the electric field, And if it is moving, it also interacts with the magnetic field as well, right? So that's the important part. And this interaction is mutual. So field somehow influences the motion of the charges. The charges also influence the fields. And so as a result, we have to discuss both of these aspects separately. Okay, I don't know if you have any questions in here, but this is essentially what it is. So why do we need the magnetic force in here? So couldn't we just get along with the electric field only and live a happy life? Uh, in any case, this is actually an interesting question. So there is some kind of a, I mean, there's some kind of a topic in I think topic is not a nice word, but in special theory of relativity, um, there are actually, I mean, you can look at the same phenomenon from a different reference frame, right? So especially if there's a moving charge, in a different reference frame, the velocity will be in a different direction, but you still will be able to actually see an electric and a magnetic force applied on the particle, right? And there are some special reference frames where this charge will not be moving, for example. The reference frame is moving with the same velocity of the charge, right? So we are going to discuss some of these relativistic issues later when time comes. But it appears that if there is an electric force applied on the charges, special relativity, special theory of relativity of Einstein actually implies that there should somehow be a magnetic force as well. But this is actually quite mathematically quite difficult to show that this is the case. But there's some kind of a strong relationship between the electric and the magnetic field. So as a result, somehow for this mathematical consistency with the theory of relativity, we should actually have two different fields, just as in the case in here. Okay, but I think at this point it is too early to talk about the relationship between the magnetic field and the electric field. So from this point on, yeah, I mean, from time to time we are just going to remember the electric field, but we are just going to concentrate on the magnetic field, right? So just keep in mind that this electric and magnetic fields are essentially two aspects of the same thing, right? Because of that, we actually call the field itself as the electromagnetic field, right? It's not just the electric field, just the magnetic field. So somehow they form some kind of a common single entity. So we actually talk about the electromagnetic force and electromagnetic energy and things like that, right? But when time comes, we are going to see the relationship between the electric and the magnetic fields later. All right, so that's actually a very long introduction, but I think this is necessary, right? So in any case, so we are in here then in this chapter, in this week, and then there are these two aspects in here. So I can talk about force on a single moving charge, or I can talk about force on a current carrying wire. I think these are two important applications of two important aspects of magnetic force and something that we actually need a lot in applications. But there are also some other, I don't know, like in plasma physics, there are these not just single moving charges, but there are many moving charges that basically create some varying current. So you can then talk about the magnetic force applied in them. But for us, these are the two important cases. Right? Somehow the book starts with this one, with the second one. they first discussed the magnetic force applied on a current carrying wire. I don't. I think they conceptually, the force on a single charge is a little bit more fundamental. We will first define the magnetic force with this, and then we are going to deduce the magnetic force expression on a current carrying wire, because a current is essentially a lot of moving charges, right? And because of that, this is my second topic, right? So as a result, I'll start with this. And in that case, I'm just going to use some kind of common sense to derive and to write down an expression of a magnetic force acting on a moving charge. So let's say it like this. So this is the, let's say, magnetic force, magnetic force on a, let me again say, single moving charge, right? So I'm just going to write down an expression. So let's just talk about what's in here. Some microphone is open. All right. Okay. So there's a charge. Well, there's a particle. Charge is just a property, but sometimes I actually use that language. There's a particle with charge Q, and it is moving. If it's not moving, then there won't be any magnetic force. And there has to be some kind of a magnetic field. So I have started with green, so let me use green in here. So there's some kind of a magnetic field. Let me show it like that. So the field is basically a field, meaning that it is everywhere. So at every point, we can talk about the value of a field. So therefore, we have to talk about the value of the magnetic field at the location of the particle. And then there's the force. So which color should I use? Yeah, I'm just going to use the white color. There's also a magnetic force in here, right? There's a vector quantity, right? So the quantity is Q is the charge. The force should depend on the charge, because if the charge is zero, then there won't be any magnetic force. V is the velocity of particle. Let's say this is the charge of particle, right? What else? There's a magnetic field. So I'm going to show this by V. There's also a complication in history, which letter you should use for representing the magnetic field. So there's also an H field as well. But I think we're going to learn about these complications later. But historically, people have used H as the letter, capital H. But this is the fundamental field, basically. So the question in here is that, what is that field? We haven't defined this. We don't know how to define it. But hopefully, when we write down the expression of the magnetic force, we will be able to see how we can define the magnetic field, right? But just like the electric field, we expect this to be a vector. And then there's this force. So I'm just going to show this by F mark. So let me keep saying that this is the magnetic force. Later, I'm just going to actually say, just call it as just force, actually. So F mag is, so the question is, right, how does F mag depend on the charge, velocity, and the magnetic field, right? And the question, the answer is, well, it should be proportional to all, proportional. right? So basically, I know that if the charge is zero, then the magnetic force is zero. Charge is the coupling constant. If there's a neutral particle, there won't be any force. Um, we have said that the magnetic force is between two moving charges. So therefore, if the velocity is zero, then the magnetic force is equal to zero. And moreover, if there's no magnetic field, so it's just the interaction between two moving charges. In that case, too, the force would be zero, right? So the force depends on all of these three quantities, and it should be, I think this is the simplest expression that we can write, but I mean, it has to be proportional to all of them. So therefore, the force is basically, the magnetic force is the product of, sorry, the charge, velocity, and the magnetic field. And here is the problem. Now we have talked about this vectors and the scalars and things like that. Charge is a scalar, we know that, but the velocity and the magnetic field, these are vectors. The force is also a vector. So somehow we have some kind of a product of two vectors in here, and that should produce a vector. So because of several reasons, it appears that this product, I mean, the product between two vectors can be only of two kinds. It's either a dot product or a cross product. In the case of a dot product, the result is a scalar, so I cannot produce any vector in here. So there's only one option in here, it's the cross product. Okay, so as a result, we basically write down the force like that, and then define the magnetic field, the concept of magnetic field as a physical entity, by using this equation, right? So I know that on a moving charge, there will be a force applied. I can directly measure this force. I can directly measure the other things as well. By using these values, I can deduce the magnitude and the direction of this magnetic field. But probably I need to use different particles moving in different directions to be able to completely measure the magnetic field, right? But this is the definition. Okay, so let's say it like this. This expression also forms the definition of the magnetic field. Okay, meaning that there are no constants of proportionality influence, right? So we just define the field like that. And so consequently, then I can discuss the units. So units of, let's say, B, you can easily see that this is newtons per coulomb per meter second. So it's Newton seconds per coulomb meter, or it is newtons divided by amperes meter. So for current carrying wires, actually we are going to, this is going to be a little bit more familiar. In any case, this is named after Nikola Tesla, you know that. And it is shown with the capital T symbol. Okay, so at this point, of course, we are just going to assume that there is a magnetic field produced. And how it is produced, we will forget about this for the time. Okay. There's the second thing in here. Let's just remember nodes. I'm reminding you this all the time, but this is necessary in here because a lot of students actually forget about these relationships, so therefore they write down the expressions in the opposite order. So, I mean, cross product actually depends on the order of the vectors. So if you just change the order, then it's going to change. The sign is going to change. So force is basically given as the charge times velocity across the magnetic field in that order. So it is not the same thing as B cross V, right? So as a result, try to remember this order in here and do not use the opposite order. A lot of directions will become important because of this thing in here. So because of the cross product in the definition, we have to use the right-hand rule all the time. Let's say it like this. Again, I'm going to say right-hand rule. I mean, in the topic of the magnetic field, whether it is the magnetic force or the field, magnetic field produced by some current carrying wire or some induction phenomenon or whatever. I mean, in all of these cases, we always meet the cross product, and so therefore we have to use the right-hand rule in all of them to actually understand the directions of some vectors involved. Right? So as a result, this is one of the things that we use a lot. So this is V. I think I'm going to use this kind of a picture in here, B. And I'm not sure if this picture can be understood in different ways. So the force would be like that, right? Which is perpendicular to both the magnetic field and the velocity. So the force is perpendicular to both of them. And so as a result, let's see. Just a moment. Yeah, we have also this right-hand rule. Let's just remember what the right-hand rule says. There are different ways of using the right hand. I suggest that you learn all of them. But when only vectors are concerned, if you have the cross product of vectors, I think the three-finger rule is the most important one. So as a result, try to learn this, right? So, but let me repeat again. So there are these three fingers, they are ordered. So that's the first, second, and the third. So the first one, well, basically, we basically order the vectors in that order. So the first finger is along the first vector. The second finger is along the second vector. And the third finger would be along basically their cross product, E cross B. Okay. So I'm just drawing, I just drew this picture for a positive charge. Right? If Q is positive. If the charge is negative, in that case, V cross B is still in the same direction, but the force will be opposite. So as a result, I'm not going to draw this picture a lot, but I'm just going to have this, I don't know, we are just going to keep using this right hand. And it is actually quite hard for me to draw these three-dimensional pictures. So as a result, I'm going to express them in the two dimensions as follows, right? So again, this is a reminder. So on a, let's say, diagrams on a 2D plane, let's say it like this. So when I draw diagrams on a 2D dimensional plane, so I'm going to express a vector which is pointing out towards us as, so let's say, vector pointing out of screen. It is towards us by this notation. And I'm going to use this notation for a vector pointing into the screen. Okay. So as a result, yeah, I don't know how my showing actually makes meaning to you. In any case, so you have to imagine this for yourself. So basically for vectors which are perpendicular to the screen plane, if the vector is pointing towards you, we are going to use this symbol. If it is pointing away from you, we are going to use this symbol. Why we are using this? Because this is like an arrow. Um, so whenever you are seeing this part of the arrow, the tip of the arrow, this part in here, you actually see the sharp tip of the arrow coming towards you. So that's an eye, all right? And if you are in here, then you are seeing these feathers at the back of the arrow. So the feathers actually look like that, right? Whatever. So in any case, in the case of a field, in which case there are vectors everywhere in space. So as a result, in that case, I'm just going to show the vector field which is pointing towards us with this arrays of dots only. And if the vector field is pointing into the screen, in that case, I'm just going to show it with these arrays of crosses, all right? So let's say it like this. This is a field into the screen. And this is a field out of the screen. Okay. So just keep this in mind, and then in lots of questions, of course, I'm going to have these or these. So sometimes I'm just going to change the directions, especially for online midterms and things like that. This is the only thing that I can do. So ask the same question, but with different directions of magnetic fields and velocities and things like that, right? So yeah, let me kind of show it like this. So this is a magnetic field. So let's say it like this. There's a uniform B pointing out of screen. Okay. Uniform magnetic field pointing out of the screen. So I'm just going to show it pictorially like that. So let's say that I'm going to pass the white color. Charge is moving in the plane of the screen. Right, so there's some kind of a charge in here, which is moving like that. So the velocity is basically is within this plane. So therefore, the velocity is perpendicular to the magnetic field. I just look at this case, right? But in reality, of course, the velocity can be in any direction, so it can also be parallel. But let's just look at only this case, okay? So is this charge positive or negative? Let's say that it is positive. Right? If it is positive, in that case, I have to use the right hand again. So V cross B is basically a vector along this direction. So that's V cross B. But since the charge is positive, Q times V cross B is also in the same direction. So therefore, yeah, I'm going to undo this. Therefore, the magnetic force in this case is along that direction. Okay. And the magnetic force is perpendicular to the magnetic field. And it's perpendicular to the velocity as well because of the cross product. So the result, this angle is exactly 90 degrees. Can we use our level for negative charges? No, you cannot. Don't use negative, the left hand. Right? Well, yes, you can, but it might be confusing. So always use the right hand for the directions. It's not just the issue of forcing here, because you're going to use this right hand a lot in all of the following chapters in different instances. So as a result, do not get confused. So always use the right hand. So finding the directional, reverting the direction of the force is actually quite easy. So that's not a big problem. Okay. In any case, if we had a negative charge in here instead of a positive charge, moving with the same velocity, in that case, the magnetic force on this one would be in the opposite direction. So yes, there's I mean, under the same conditions, the force on the negative charge will be in the opposite direction. And this is actually consistent with what we also see for the case of the electric force as well, right? Positive charges, forces like that, let's say forces like that. Zero charge, force is zero. Negative charge, force changes direction. We have the same kind of a thing in here. So if the, I don't know, if the particle had zero charge, then the magnetic force would be zero. And so as a result, if the charge changes sign, the force also changes direction. That's actually quite consistent with the linear behavior. Okay, so in any case, as a result for that case, I mean, for that kind of a picture, we have these three vectors which are perpendicular to each other. All right. Why did I start discussing this? I think this is kind of important in here. Right. I think I'm going to discuss the cyclotron motion next. But let's just note one thing here. This is a little bit more general. So that's the power of magnetic force. So let's just remember this. This is the power of the magnetic force. So it's basically magnetic force dotted with velocity. So let's just remember that this is the rate of change of the work done by the magnetic field, right? So it's not the rate of change, it's the rate of work done by magnetic force. So there's a magnetic work done. It's the work done per unit time, right? You can understand it like that. And we know that therefore, I mean, we know the expression for the work done. And if I just divide by this time interval, the displacement is divided by the time gives us the velocity. So the power, the instantaneous power of the magnetic force is given like this. But since this is a cross product, the force is a cross product, and the cross product is perpendicular to the velocity. Force is perpendicular to velocity, so therefore their dot product is going to give you zero. Right? So that's actually quite a striking thing. It basically tells you that the magnetic force doesn't do any work. Doesn't do any work. All right. This is kind of striking and physically confusing as well, because later we are going to see that the field itself has energy. And sometimes this energy is transferred to the charged particles. But when transferring energy, I mean, energy is not directly transferred by the magnetic force. It's actually transferred by some other mechanism that we are going to see later, right? I don't know if I'm going to discuss this, but we will see later. We will be talking about magnetic energy and things like that. So starting with this week, actually. So we are going to see a magnetic energy concept within this week. But in any case, at least for this case, when we consider the magnetic force applied on a charged particle, the magnetic force doesn't do any work. And so as a result, you expect that if if the magnetic force is the only force acting on the particle, the speed of the particle doesn't change. Right? So let's say in here, so if the magnetic force is the only force on the particle, in that case, then the kinetic energy of particle is constant, which means speed is constant. Speed doesn't change, right? So that's constant. Velocity changes, but the speed doesn't change. So this implies that at least for this motion, this particle basically does a uniform circular motion, right? It's a circular motion where the speed is constant. Well, it's a motion where the speed is constant. The velocity changes direction. And well, all of the conditions are right in here. So therefore, you can easily see that this thing is actually doing a uniform circular motion with constant speed. Okay. So as a result, I'm just going to talk about this motion here. So that's called the cyclotron motion. Let's say it like this. I'm going to explain why it is called cyclotron motion. Cyclotron is one of the first particle accelerators, oldest. But essentially at CERN, for example, they are using particle accelerators, which are called synchrotrons. It's just a modification of the cyclotron device, right? So as a result, this motion is important in that case. So as a result, this is called the cyclotron motion. But in any case, it's basically the circular motion. So next, I'm going to talk about this cyclotron motion, right? So again, it's the same situation. We have some kind of a uniform magnetic field, and we have a charged particle moving in a plane perpendicular to that magnetic field. Right? And so the uniform circular motion of the charged particle is called the cyclotron motion. But let's have a break in here, and we'll continue after the break. So let me first stop the recording.